Let's talk a little bit more about thermal zones and how we define them and what they're for. So, the basic idea of a thermal analysis is we're separating the outside, so nature, the climate, the exterior climate, from an interior climate, something that's inside a building. And that's really a very basic definition of a building, right? Is we're creating a different environment inside of it. So, a very basic and defensible initial thermal analysis of a building would be a single zone. A lot of houses are definitely single zones because it also, if we're really designing zones for buildings, it's going to be about uh, first of all how the space is used. Is it a lobby and it's got this many people in it, or is it a mechanical room or a server room that's got all this heat coming out of it? Um, and what is the demands that we need to supply for heating and cooling to that space. So that's really what thermal zoning is. Slightly different in a thermal analysis because we have other variables we're thinking about maybe, but the point is it's not really rooms. Okay, so it's not just you say, here's my floor plan, I'm going to make thermal zones for every single room. That doesn't really make sense because the idea is that we create a separate thermal zone if there is a reason to change our thought about what's going to happen with heat or with the internal environment between these two volumes of air, basically. So right here, then I have um, a single polysurface zone that I can run as uh, I could make this into a zone right now if I want to, and I'll just give it whatever template. And now I have a zone that I could actually do a thermal analysis of. Let's see what's inside of it. We have basically four facades, an exterior floor, and a roof. And where are these coming from? These are coming from the envelope section of the model. And um, Climate Studio knows through context of geometry how to define each of these surfaces. So, something at the top of the building that's horizontal or angled is going to be a roof. A facade is, sorry, let me click that. It is, you know, essentially a horizontal, I'm sorry, a vertical wall or something we would call a wall that's that's touching exterior air. Um, a ground slab is a horizontal surface or a surface that's touching the ground. That's a floor, and then a ground wall would be a wall, so a vertical surface that's touching ground, right? So anyway, there's just a bunch of um, conditions that are defined by the modeling platform um, as to how to consider these different how heat's going to move through different surfaces in the zones we create. And so then we could also, I'm going to delete this zone. We can take the same volume, right? But now I have two, I want to say there's two different thermal zones here. So I can create these. And essentially the only difference is going to be that, um, oops, sorry, that we have a partition here. So you'll see we have the same facades, but that this surface that separates the two internal zones is a partition now. And then we still have an exterior floor in each zone. And then if you come to the zone next to it, it's exactly the same layout with the partition, exterior roof, and the floor. Um, and then if we wanted to further subdivide this, maybe we have a corridor or something or a uh, stair core that we think is going to have a different thermal properties, then we can create three zones. And then now the third zone is going to be all partitions. Open the zone. See, these are all partitions now because they're all inside, and all they're not facades because they're separating interior zone from another interior zone. So that's the basic idea of the geometry for thermal zones. Um, well, and then there's two other things. Then if we say, okay, now what if it's not my zone is not touching or my surface is not touching air, it's actually touching, for example, here we're going to say it's touching the ground. Oops. And the ground's just a different thermal condition, right? It's not air. It's going to have different temperatures and other variables. So I'm going to turn the ground then into a ground surface. And we see then that that ground surface is now an addition to the interior zone. So if I come back here and I look at my zone, let me just, I'll look at one of these zones. Which one? This one. Um, I still have an exterior floor, right? But then beneath that exterior floor is what it's touching, which is this ground boundary, right? So the thermal zone is determining what's inside and how it's relating to the outside, and then you can say what's outside, so that the default outside is air. If we say it's not air, then we have to create ground, or we can create what's called an adiabatic surface. What is that? So if I now come back and I add, let's say I want to say that this portion of this building is touching another building. I don't have any control over that building, and I'm not going to model it. It's not part of what I'm designing or maybe it's a part of a building that's already built or that I am controlling, but I want to separate out my thermal model. I can say this is an adiabatic surface, which simply means we're saying that for the purposes of um, my model, I don't want I want to assume that there's no heat moving through that surface. So in a way, partition walls are essentially, if these two zones that are separating this partition wall is separating have the same thermal properties, then that's an adiabatic surface because no heat is going to move through them, um, through that surface. But if we, it's possible that if this were a server room and had a bunch of heat, um, being produced here, and this was, an office, maybe this wouldn't be an adiabatic surface. There would be some kind of transfer, it just wouldn't be to the outside. So an adiabatic surface is basically saying we're going to just basically cap off our thermal model here and say nothing's happening at that surface. Okay, so that's the basic categories. And so if we then look at, here's the model that I've been using as my little sample for exercise 2 and 9. Um, I decided to model this where I had all the rooms for all the apartments available to me, but that doesn't mean I should make them all zones, and that's actually I didn't. I modeled the apartments as individual, complete, single units. Um, it's probably good to have different the ability to set a top apartment different than the apartment below it, because we have air up here and no air down there. We might have a different HVAC setup for that or whatever. And I want to be able to come in, so I did model my individual rooms in case I wanted to, like one thing we did in one situation was to add an exhaust fan in the kitchen, and so that allowed me to add that exhaust fan only in this volume. Um, and then the idea was to run these, so to like run this as one zone initially, all of these spaces, but they're all part of the building because they're all separate. We're saying there's a different environment inside all this space than what's out here. Um, and then I said, okay, and I gave you some templates to create that you use as the baseline or as the templates to run the thermal analysis. And then I said, well, now go and start thinking, well, does that make sense? Are there spaces that maybe should have different thermal settings? And like the most immediate one that I think is like this lobby doesn't, I don't think that a lobby and an apartment are going to have the same thermal properties, right? There's a lot of different people. The use type of the lobby is different. I bet you the HVAC is going to be different, and the amount of heat coming off of people and the lighting is going to be different. So then I was saying, why don't you go into, so if I come into my, um, well, we can just even look at the names here. So what I did By the way, these, just so you don't get confused, where it says single family here, that's because um, I made templates for the house that were single family, and then I just used those and adjusted them for my purposes here. But the basic point here is you can see that, so for all my apartments, I have single family, um, like a single family home template. And then for things like the stairs, I went and found other templates that I thought would more accurately reflect what was going on. And I'm just playing around. I'm not saying this has to be accurate, but so for example, my stair core here, I found a template um, that was it's a medium office stair. It has, for example, the people density they're claiming is zero because there's just not that many people and they're they're not there very up there very often. There's no equipment in there, so that's going to really change its thermal properties. Um, the HVAC system might be set differently. There's probably no. No, they do have a. Let's see, no, they don't have any mechanical ventilation. It looks like, which makes sense because maybe there's no ducting in there. Whatever. I just wanted you to then go find in this giant list of templates um, something that, the easier way of doing it is we would apply it here. I would go apply template and then put in 90.1 because I was asking you to find 90.1 templates and just start looking through here and seeing if there's things that make sense. Remember, CZ4 would be climate zone 4. That's where New York City is. Um, and trying templates that are set for different type for the type of space that your zone is representing, and then running simulations and seeing if you come up with any difference in the outputs, and if so, um, talk about them. So, for example, mine. Um, So here's, I use that, the 90.1 cavity. So that was the energy code cavity template that I gave you guys. Um, and this is for the full building. Then I did it where I changed to apartment and lobby zones. And I got a significantly different site EUI doing that run, right? So I'm basically saying that this zone and these apartment zones were the same in this run, I'm sorry, in this run, and then different in this run. Oh, I'm sorry, same in this run, different in this run. Um, and then I did the same thing. I found mechanical room, stair cores, etc., and I just experimented with setting these zones to having different thermal properties by just choosing templates. The final thing then to say is, let's say, because I can't remember which assignment exactly, it doesn't matter. Let's say I had this house that I was, that I wanted now to turn into an apartment, and I was going to stick it into this apartment building, right? So now, um, this house here is this unit right there. Um, so if I wanted to do that without having to design the entire apartment building, I could. So that, in other words, I'm saying I want to approximate this situation here without having the apartment building. That's when I would use adiabatic surfaces, and I would come in. Let me turn off this the overhangs here. Um, then I would say, okay, I'm going to create surfaces wherever um, there would actually be a building. I'm going to turn this into an adiabatic surface, and so now, that I'd have to delete all these zones. Well, I'll go ahead and do it because I just want to save this. So if I delete all these zones, this interior boundary now, um, it's not there because this isn't a zone. Let me see if I can make this work really quickly. I'm gonna just make this a zone. Yeah, so now we're seeing these are all the windows because when I deleted the program's remembering that I had windows, and I just selected all these. Anyway, don't worry about the red. You can see now that I had this adiabatic boundary here. as part of this analysis. So I could go in and add those all the way around the building. I could put them on the floor and the roof or the ceiling, and then basically create a simulation similar to the complete simulation that I was doing before with the entire building. So that's one way to use adiabatic surfaces. If you have a full building, you wouldn't need them because they would become, this would be a partition wall, right, instead of an adiabatic surface. All right, I hope that's helpful. Let me know if you have any questions.